acid-base titrations. So titration is a technique where we're determining an amount or a concentration of something that's unknown. So we're going to use a solution with a known concentration. We're going to react it with a solution of unknown concentration. In an acid-base titration, one of these is an acid, the other is a base. As we add the known solution to the unknown solution, we're going to monitor the pH. In Chem 1A, we monitored that with an indicator, phenolphthalein. When the pH switches from acidic to basic, the phenolphthalein changes color, and that tells us to stop. We can also monitor it with a pH meter, which is what we'll be doing in our next experiment. So the equivalence point is where the moles of acid is stoichiometrically equal to the moles of base. It's not necessarily equal. If you have diprotic acid, it's going to be a 1-to-2 ratio instead of 1-to-1, whatever the stoichiometry is. And so at the equivalence point, we can measure the amount of known solution that's been added, and we can calculate the concentration of the unknown solution. So here we have sodium hydroxide in our burette and an acid in our flask. As the sodium hydroxide is added, it reacts with the acid, neutralizing it. When we get to the equivalence point, we've added enough sodium hydroxide to react with all of the acid molecules. So we're going to start out with a clear solution. Technically drinkable, yes, with most acids. And so here, as you're adding it, you may see this a little bit of a pink swirl here because the concentration is greater right there where the sodium hydroxide is entering. But when you swirl it and mix it together, the pink color goes away. At the end, the pink color doesn't go away. This is a very intense pink, right? And I just want to emphasize the exact color that you get is less important than how much of the known solution was in the last addition. If you added 1 drop and it went from colorless to bright, bright pink, well, you are no more than 1 drop off of the equivalence point, which is like 0.02 milliliters, right? So that's pretty close. If you don't know how many drops you added and you get a bright pink solution, you should probably do that one over again, right? But the color that you end up with here is also affected by how much indicator you put in the solution, right? If you put very little indicator in there, you could probably add tons and tons of base and only get a pale pink. Of course, you don't want that to happen because we're not so concerned about getting the pale pink color. We're concerned about getting a correct result, right? So if we are monitoring the pH with a pH meter, then we can plot the pH versus the volume of sodium hydroxide added. And we'll see a curve like this. The pH starts out low because this is an acid, and as we add the sodium hydroxide, it increases. When we get to the equivalence point, the pH is going to be shooting up, and it'll come up here because now we have a basic solution as we add more and more sodium hydroxide. So this particular curve is looking at the titration of 50 milliliters of 0.1 molar HCl with 0.1 molar sodium hydroxide. The equivalence point here is the point of inflection on this curve, which is where the slope changes from positive to negative or negative to positive. Let me think about that. Okay, we thought about this, got a little help. So the inflection point is where the slope stops increasing and begins to decrease. And so that's that point right here. The pH is going to change very quickly there. The exact shape of this curve will depend on a lot of things, including the acid and base strength and their concentrations. So we are going to walk through the titration of a strong acid with a strong base. So we're going to consider the titration of 25 milliliters of 0.1 molar HCl with 0.1 molar NaOH. So the first thing we're going to do is we're going to calculate the volume of sodium hydroxide needed to reach the equivalence point. And we can set this up as a solution stoichiometry problem. We know we have 25 milliliters of HCl, and it's 0.100 moles per liter. And we have 0.100 moles per liter of the sodium hydroxide. And so we could take our grams to moles to grams, grams to moles to moles to grams, and modify that. We're starting out with volume and ending with volume. But the numbers on this one are simple, and they were made that way on purpose. The concentrations of the acid and the base are equal. If we want equal moles of acid and base, then what can we know about the volumes? They would also have to be equal, right? So we're going to need 25 milliliters of the sodium hydroxide to reach the equivalence point. But let's just pretend our numbers weren't very good. So we've got 25 milliliters of HCl, and that's 0.100 moles per liter. And then the stoichiometry here is 1:1. So 1 mole of sodium hydroxide per 1 mole of HCl. And then 0.1 mole per liter of the sodium hydroxide. So people think about the units here differently. I think a lot of you have gotten comfortable with just changing milliliters into liters and going back and forth like that. But I would like you to try to embrace the concept of the millimole. We talked about that before. So here's milliliters. This is the concentration in moles per liter. If I do the same thing to the top and bottom of a fraction, I'm not changing its value. Right? If I multiply the top by 2 and the bottom by 2, the 2's would cancel out, right? So if I multiply the top by milli and the bottom by milli, it's the same. So now I have milliliters canceling milliliters, that gives me millimoles. Well, I can do that to the mole ratio as well, and to this other concentration. And so I can get to milliliters without converting back and forth. Any questions? This is the sort of thing we learned how to do in Chem 1A. just in case you don't remember. We did do that. Okay, so now we're going to construct a pH curve by calculating what the pHs are. So what is the initial pH of this solution before we add anything? How would we figure that out? We have a strong acid, right? So with the strong acid, it ionizes completely. And so our hydrogen ion concentration is equal to the acid concentration. And so pH is the negative log of 0.10, which will equal 1.000. Okay? So on the graph here, they put a dot at pH 1 and 0 volume of sodium hydroxide added. So let's see what happens after adding 5 milliliters of the sodium hydroxide. Now, this is where things get a little more complicated because the volume in the flask has changed, right? So we have to do this stoichiometry part, which again, I don't like how they do that. I probably should have made a note of what that number was before I crossed it out. 3 zeros and a 5. So here, adding this many moles, how did we figure that out? Well, 5.00 milliliters times 0.100 moles per liter. So that's going to give me 0.500 millimoles, or 0.000500 moles. It's easier when you're doing these things if you use millimoles, because otherwise you're going to have all of these numbers that have a bunch of zeros in front of them. And yeah, you can put it in scientific notation, but that's kind of a pain also. I prefer 0.5. It's just nicer. But we're looking at moles here and not millimoles. So we're adding this many moles of sodium hydroxide. And so that is going to result in us reacting all of the sodium hydroxide, and that's going to react with the same amount of the acid, right, hydronium ion, which will leave us with 0.00200 moles of hydrogen ion or hydronium ion. To know the pH, we have to calculate the concentration, the molarity. So this is our moles of hydronium ion, so that's right here. But we're going to divide by the total volume, the initial volume, plus what was added. That make sense? And so that gives us this concentration, 0.0667. And so then the negative log of that is 1.176. And they graph that right here. This is 25. So each of these lines represents 5 milliliters added. Any questions? So we're doing this now with a strong acid and a strong base. And next we're going to do it with a weak acid and a strong base. And that's going to throw some other considerations in. So it's really important to understand this one as we go along, because then we're going to add something to it. Okay? So what would the pH be after adding 10 milliliters, 15 milliliters, 20 milliliters of sodium hydroxide? Well, they did these calculations for us. Oops. 1.37, 1.6, 1.95. Those would be calculated in the same way. Like for the 15, we're going to take 15 milliliters. Oops. 15 milliliters, and it's 0.100 moles per liter. So that's going to give me 1.50 millimoles, or 0.00150 moles. And then I'm going to look at, that's my hydroxide reacting with the hydronium. So I've got 0.00150, and I originally had 25 milliliters of that. 0.0025. Is that right? And so then all of this is going to react. And this would be my moles of hydronium ion. And then I have to look at what is the total volume now. Well, my total volume is what I started with, the 25 milliliters, plus the 15 milliliters of sodium hydroxide that I just added. So that's 40 milliliters. Yes?
How did that end up being 0.02 moles?
That's a good question.
Math and math.
That was bad math. Thank you. Bad math can happen to anyone. 1. Better? We hopefully would have figured it out eventually, but. So our new hydronium ion concentration is the moles of it divided by the volume in liters and then we're going to take the negative log of that number, and we're going to get the 1.6. The same process that we did with the first one. And they're giving these to us so that we don't have to do the same calculation over again 3 times. Did one of them because it's kind of helpful to see it again. So here we've got those points graphed. Is this what we expect to happen as we add sodium hydroxide to an acid? Yeah, we expect it to become more basic, right? We're neutralizing the acid. Okay, so what happens at the equivalence point? So here at the equivalence point, we originally started out with 0.025 moles, and now we've added 0.025 moles of sodium hydroxide. And so that's all going to react and give us a hydronium ion concentration of 0, right? Can you have 0? No.
But you can have drinkable levels.
What would it be? It would be neutral, and what is the hydrogen ion concentration in pure water? 10 to the minus 7. Yep. So this is going to be 1 times 10 to the minus 7. And so the pH will be 7. Because when you reach the equivalence point of a titration between a strong acid and a strong base, all of the hydrogen ions from the strong acid have reacted with all of the hydroxide ions from the strong base. And what you have here is salt water. You have a solution of sodium chloride. And yes, you could drink it. It's not going to taste very good. Any questions? Well, in 1A, that's where we stopped. But we're not going to stop there anymore. We're going to keep going. So here, adding 30 milliliters of sodium hydroxide. So that means I'm going to have 0.00300 moles of my sodium hydroxide, and I'm going to have 0.00250 moles of my hydronium ion. When we do these calculations, we are not adding this on to a previous calculation. It doesn't matter if we're adding the 30 milliliters all at once, or if we did it in 5 mil increments and saw what happened in between. We're just interested in how much total sodium hydroxide have we added. So we've added 0.003, and the hydronium originally was 0.0025. Now which of these is smaller? The hydronium ion concentration is smaller. So now this is the limiting reactant. So all of that is going to react, giving us essentially 0. And we're going to react 0.00250 moles of our hydroxide, giving us this much.
0.5 millimoles.
Yeah, that would be 0.5 millimoles. So we want to calculate the pH. Well, we have information about the hydroxide ion. So we need to find the concentration of the hydroxide ion. That's going to be the moles of hydroxide ion divided by the total volume, which if you're doing it in liters, it's going to be 0.0250 liters plus 0.0300 liters. So that's the hydroxide ion concentration. Remember the circle of pH? So we have hydroxide ion concentration. We want pH, which is on the opposite side of the circle. We could take this and calculate the POH, subtract that from 14, and get the pH. That's what I prefer doing. So POH is a negative log of the hydroxide. I said it right the first time. Two point four, no, 2.0. 2.0414. And I think 2 sig figs is appropriate here. pH then equals exactly 14 minus 2.0414. With 2 sig figs, that'll be 11.96. And that was a big change, right? We went from 7 all the way up to 11. But the previous one was also big. We went from 2 up to 7. So near the equivalence point, the pH changes dramatically. Any questions? So we can go on and continue this and see, well, what happens when we add 35, 40, 50 milliliters of sodium hydroxide? And do the same calculation we just did. You'll find the moles of sodium hydroxide added, and you'll see how that reacts stoichiometrically with the moles of HCl added. Now hydroxide is going to be left over. You take the moles of hydroxide and you divide by the new total volume. Okay? So now we get 12.22, 12.36, 12.52. Any questions? So this is an overall pH curve. So we have our initial pH here when we've added no sodium hydroxide. This region before the equivalence point, we have an excess of hydronium ion. The equivalence point for strong acid, strong base titration will always be at 7. And then afterwards, we have an excess of hydroxide ion. What if we titrated a strong base with a strong acid? That can be done also. Well then, we're going to start with a high pH because we have a basic solution and we're adding acid to it. And so the pH is going to decrease slowly until we get to the equivalence point, which again is going to be at 7. And it will continue to decrease, and then it'll level off. And so here we have an excess of hydronium ion. We started out with an excess of hydroxide ion. Any questions? A 50 ml sample of 0.2 molar sodium hydroxide is titrated with 0.2 molar nitric acid. Calculate the pH after the addition of 60 milliliters of nitric acid. Always a good idea to look at the chemical equation between the acid and the base. This is 1:1. So we're going to look at, we're adding nitric acid, so we're adding hydronium ions or hydrogen ions to the initial hydroxide ions, and those are reacting to form water. So we had 50 milliliters of 0.2 molar sodium hydroxide. 50 milliliters times 0.2 molar is going to be 10 millimoles. So I'm starting out with 10 millimoles of hydroxide. And I'm going to see, well, how much acid did I add? Oh, do this down in the corner maybe. So we added 60 milliliters of 0.2 molar nitric acid. So 60 times 0.2 is 12 millimoles of acid. So I'm adding 12 millimoles of acid, and I'm looking at the stoichiometry of this, which is limiting the hydroxide, right? So that means that all the hydroxide will get neutralized. So we'll lose 10 millimoles of that. We will lose 10 millimoles of the acid when we're doing that. And we're going to end up with 2 millimoles of acid left and essentially 0 millimoles of hydroxide. I need to find the concentration of hydrogen ion to find the pH. So I've got 2 millimoles, and I'm going to divide that by the total volume, 50 milliliters plus 60 milliliters. Zero point 0.01818 repeating. If you don't like millimoles, you can do it in moles. There's just a lot more zeros. So that's equal to the hydrogen ion concentration. You have to pay attention to what you're doing here, because sometimes you'll have hydrogen ion concentration, hydrogen in excess, and sometimes you'll have hydroxide in excess. And so you can't just assume that it's going to be one or the other. So then my pH is a negative log. .74036. We could argue about sig figs here. What would a reasonable number seem to be? 3? So 1.740. It's actually going to be 2, but 3 is close enough. There's this subtraction here that got us down to 2, right? But that's not something we're going to stress about. I don't want you rounding this to 2. That would be bad. That's no significant figures, right? If you're not sure, write an extra one, because you can always knock it off later. So this would have a pH of 1.74. Any questions? Yes?
You subtracted the 10 millimoles because it had the smallest concentration?
Yes.
Okay.
Yeah, I have the least amount of the hydroxide, so all of that is going to get used up. And so I'm going to have 2 millimoles of the hydrogen left. The individual pieces of this are not hard. But putting them all together and doing a problem like this on your own can be challenging, right? So you have to practice, right, until you become comfortable with it. But you'll get there. Any questions? .74. The amount of strong acid in the flask shown here is to be titrated by a strong base. Which mark on the burette next to the flask indicates the amount of base required to reach the equivalence point? And here, yes, we are counting circles.
Is that how you do it?
That's what we're doing. So we have 1, 2, 3, 4, 5, 6. We have 7 hydrogen ions in there. How many hydroxide ions do we need? 7. 1. Come on, pointer. 1, 2, 3, 4, 5, 6, 7. So the answer is D. Sometimes questions like this, when you're used to doing complicated calculations, can really throw you. It's D. And we're going to stop here.